Hello and welcome to this session on generators at Drax Power Station. We have 6 generators that generate electricity at 23,500 volts. Each generator can produce enough electricity for 1 million homes, but how is this done? The generator is made of 2 parts. The middle, which is called the rotor, is a giant cylinder-shaped electromagnet. This is attached to the turbines and will spin at the same speed. The second part, which is also the outer casing, is called the stator. It surrounds a spinning electromagnet and is made of copper bars. That is essentially the basics of the generator, but we need to dig a bit deeper to explore the science. Let's start by looking at some facts on the humble magnet. First of all, magnets have 2 poles, north and south. All magnets have a magnetic field which exerts a non-contact force on other magnets and magnetic metals like iron, steel, nickel and cobalt. The closer a magnet gets to the materials, the stronger the force of attraction is. This is seen in fridge magnets which stick to the fridge only when held close to the metal surface. We can see the magnetic field in this diagram. Notice that the arrows always go north to south and show the effect the field would have on the North Pole. You can also think of the poles as having 2 different charges, with the north being positive and the south negative. You can see the effect of the magnetic fields when you try to put the poles of 2 magnets together. Therefore, if you try and put 2 north poles together, the fields are pushing against each other and will repel. No matter how hard you try to push them together, they will not attach to each other. Whereas, if you rotate one of the magnets so the north and south poles are facing, the field arrows are going in the same direction and would allow attraction and happily stick together. Copper is a conductive metal, which when moved within a magnetic field will generate electricity. How does this work? We need to delve down to the atomic level. The nuclear model of atoms consists of a nucleus surrounded by orbiting electrons. The nucleus consists of protons which have a positive charge, and neutrons which are neutral and have no charge. Orbiting around the nucleus are the electrons which carry a negative charge. The atomic number of copper is 29, which is the number of protons in the nucleus. In a neutral atom, that also equates to 29 electrons. The electrons are arranged in orbiting energy levels, with the outer layer only having 1 electron, which is known as the valence or free electron. If enough energy is applied to the free electron, it will leave the atom and bounce around until it finds another atom to join, which in turn ejects that atom's free electron. This process, with the free electrons moving from one atom to another, happens many times when producing electricity. Copper is particularly conductive because the bonds holding the free electron in place are relatively weak and therefore do not need a huge amount of energy to break free. We have looked at the materials we need to make electricity, but we also need to add one more factor, and that is movement. The key to starting the process is the stored energy in the magnetic poles. Earlier we said you could think of the poles in the terms of a positive north and a negative south. In this video you can see a copper coil spinning in a magnetic field created with 2 magnets. One side is a north pole, the other side a south pole. As the coil moves towards the north pole, the free electrons in the copper are attracted to the positive charged pole. Then as it spins towards the south pole, the free electrons are repelled by the pole's negative charge. This push-pull movement creates electricity. The movement of the copper in a magnetic field creates electricity. If the movement stops, so does the electricity. To generate on a large scale, you need continued movement. The generators at Drax use this basic principle, but we switch it around. Instead of spinning the copper coil, we spin an electromagnet surrounded by a static copper coil. Our electromagnets are what's known as an induced magnet. This means we create the magnetic field using an alloy steel core with copper wire wrapped around it. A current runs through the copper wire, creating a magnetic field. The core, which is cylindrical in shape, is effectively split in half along its length. One half is the North Pole, whilst the other half is the South Pole. Why do we use an induced electromagnet? Well, our electromagnets are huge, 18 meters in length and weigh 82 tons. We also need a very strong magnetic field that we can control, turn up, down, on or off, which we would not be able to do with a permanent or normal magnet. What's current? Current is the term for the flow rate of electrons and is measured in amps. Basically, it's a number of electrons moving past a single point in a set amount of time. Here's a crazy fact for you. 1 amp is equivalent to 6,242,000 billion electrons per second. Another way of thinking of current is like the flow of water in a river. The more water flowing or the faster the flow, the higher the current. So how does running a current through copper create a magnetic field? It's a little bit like magic. The magnetic field is produced by moving electrons in the copper, which are activated by the current. Turn the current off, the movement of electrons stops, and the magnetic field stops. At Drax, when we generate at full capacity, the generators are producing 19,000 amps. Good luck trying to work out how many electrons that is per second. As we saw earlier, we have a rotating magnetic field produced by the spinning electromagnet. This will generate an alternating current, which means the current changes direction depending on which pole is exerting its influence on the electrons in the copper. It will show a profile like this, which can be viewed using a machine called an oscilloscope. As you can see, the red line goes through zero after each pole has rotated round. This is not practical for large-scale generation, as zero equals no output, which would give a fluctuating electricity supply. Nobody wants flickering lights or electrical gadgets which stop and start all the time. Therefore, we need to stagger the generation, so you never have a period with zero output. To enable us to do this, we use 3 sets of copper bars in the stator part of the generator. They are in a staggered formation in the outer casing surrounding the electromagnet. This enables Drax to generate 3-phase electricity.
As you can see in this graphic, staggering the phases means that there's always an output from the generator. There is still some flickering, but the rotation of the magnet is so fast that it is not discernible to the naked eye. Frequency is the number of times
The alternating current completes a forward and reverse cycle. This oscillation is measured in seconds and is known as Hertz or Hz. In the case of our generators, it's the number of revolutions of the magnet in a second, which is 50 per second or 3,000 per minute, and equates to electricity generated at 50 Hertz. As well as frequency, supply and demand of electricity is also important. Demand is users like you and me and the amount of electricity we are using during the day or night. If there is too much demand and not enough electricity being generated, then frequency will fall. On the other hand, if there is too much electricity and not enough demand, the frequency will rise. As we all know, humans are nothing if not unpredictable. Therefore, balancing supply and demand is not an easy task. At Drax, we change the generation frequency and electrical output to match demand. This is very reactive, with response in less than 1 second after the frequency change is detected. So what do you think could happen if we cannot match supply and demand? As well as flow, electricity also needs power or push to move through the wires. This is known as voltage or electric potential difference. High voltage is needed to push electricity from the different electricity generators to anywhere in the UK. We generate electricity at 23,500 volts, which sounds powerful when compared to the voltage in our homes, which is typically 240 volts. But at 23,500 volts, the electricity is not strong enough for the transmission grid, which is a pylon network that covers the UK. The grid transmits electricity at 400,000 volts, which is enough power to transport electricity throughout the country. So how do you increase or decrease the voltage in electricity? Transformers are used to increase or decrease the voltage in electricity. A transformer consists of an iron core and a series of windings. These are coils of copper wire wrapped around each side of the iron core. One side of the core has the input voltage. This is known as primary. The other side has the output, which is known as secondary. Each side will have a different number of copper coils, depending on whether the electricity is to be increased, stepped up, or decreased, stepped down. To step up the voltage, the secondary side needs to have more coils than the primary. We step up the voltage, increasing the power so that there is enough push to enable the electricity to travel round the UK to meet demand. Before the electricity reaches domestic supply, it is stepped down so it is safer to use in our homes. Thank you for listening to this session on generators. There now follows 5 questions to test your knowledge. Question 1. What is the chemical symbol and atomic number of copper? Is it A, CO29, B, Cu29, 3, CO39, or D, Cu39? Question number 2. The spinning electromagnet generates what type of electrical output? A, direct current, B, strong current, C, alternating current, or D, highly controlled current? Question number 3. What is electrical current? A, a lively dried fruit, B, the power of electricity, C, the frequency of electricity, or D, the flow of electrons in a wire? Question number 4. What does a transformer do? Is it A, increases or decreases electrical voltage, B, change from a car to a robot, C, name of the process to make batteries, or D, makes a speaker transmit sound. And the last question, number 5. What is the voltage of the electricity before it goes through the transformer? Is it A, 400,000 volts, B, 19,000 volts, C, 240 volts, or D, 23,500 volts? And now it's time for the answers. Question 1. What is the chemical symbol and atomic number of copper? The answer to that is B, Cu29. Number 2. The spinning electromagnet generates what type of electrical output? That's C, alternating current. Number 3. What is electrical current? And that's D, the flow of electrons in a wire. Number 4. What does a transformer do? And that's A, increases or decreases electrical voltage. And finally, number 5, what is the voltage of the electricity before it goes through the transformers? And that's D, 23,500 volts.